So good morning to everyone. Welcome to this open presentation of the open call of the BIOMAC project. I'm Giulio Poggiaroni from EUBIA, and I will moderate this session. So a few housekeeping rules. Please use the chat and Q&A box to post your question. We will have a series of presentations introducing the open call that it's going to be launched tomorrow. So application will be able to flow from tomorrow onwards. And at the end, we will have also direct Q&A sessions when you can raise your hand and we will allow you to pose an oral question, or you can just type in your question. I will share in the chat box soon the link to the website if you don't have it yet, and the link to the dedicated page of the open call. So without further ado, I will give the floor to Professor Bikiaris from the Aristotle University of Thessaloniki, which is the coordinator of the BIOMAC project, who will give us a brief introduction of the BIOMAC Open Innovation Testbed, and then we will follow with the other speakers. Professor, the floor is yours.
Thank you very much, Giulio. I will try to share my screen to start the presentation. At the moment, it's not possible.
Now you're allowed.
Okay, now, okay, thank you, Giulio. Okay. Good morning to all. I'm Dimitris Bikiaris, professor at Aristotle University of Thessaloniki, and I would like to thank you all for coming to this webinar. Okay, I don't know why it doesn't go. You can see the first, yes?
It's the last one.
The last one. Okay, now you can see the first.
Yes,
okay,
try to put it full screen.
Full
maybe.
Screen. Okay.
Okay, it works.
It works. Our group is coordinate the European Biomass Nanomaterials Community. Is one of the 4 OETBs project running now at the moment in EU. We are in the mid of our project with a lot of work that has been done from all participants, and now we are ready for the next step, which is the most important milestone, let's say, to open the open call of Open Innovation Test Bed. You have seen previously the agenda of our webinar meeting. I will try to introduce the BIOMAC. After the pilot lines will introduced by Professor Kostridafilidis and Georgia Aranio, exploring the OETB transfer service hubs by Eleonora Di Maria from University of Padova. The 5 BIOMAC test cases will be presented from Professor Daniel Smith from LIST, and how to apply the open call by Annika Frank from IBB. And of course, we have some time for questions at the end of the project. Starting, what is an OETB? It is an entity offering access to physical facilities, capabilities, and services required for the development, testing, and upscaling of nanotechnology and advanced materials in industrial environments. The objective of the Open Innovation Test Bed is to bring nanotechnologies and advanced materials within the reach of companies and users in order to advance from validation in laboratory, TRL4, to prototypes in industrial environments, so we have to go in TRL7. It aims to develop, test, and upscale nanotechnologies and advanced materials. You will see all of these materials that we produce in our project, nanomaterials, and of course, innovative polymers, nanocomposites for several applications. We have 5 test cases here in our OETB. What is so special about an OETB? We provide a complete holistic service via a single contractor, the single entry point. IBB is responsible to create this single entry point, and Annika will present some information at the end of this webinar. It comprised of a and expert scientists from all over Europe, offering their expertise and infrastructure at competitive prices. We are 34 partners to this project with a lot of activities. Substantially reduced time and cost to progress from an idea to a successful project, and of course, integrated business and marketing services to help with access to financing opportunities and reaching out to new markets. Let's see first what is the BIOMAC project in a nutshell. Is a Horizon 2020 project that will establish an open innovation test bed, and that's why this is the aim of this webinar today, where technologies and solutions utilizing nano-enabled bio-based materials will be upscaled and prepared for market application. We finished so far our upgrade of pilot lines. Professor Todafilidis will present and all these pilot lines. And the overall ambition of BIOMAC is to boost and sustain innovation in the field of European bioeconomy industries by reducing the time to market of novel nanotechnologies, thus reducing cost and risk. So all of this work that we will do in our BIOMAC project will use from several SMEs companies, startup companies, and other companies. And all these novel technologies that we will produce will become available to all scientific and industrial community. As I said, we are 34 partners with a budget close to 17 million. This is the total budget. About 40.5 million is the funding from EU. AUTH is the coordinator of this project, and we have a very good management team with AUTH, STAM, University of Padua, Excelsis Lubia, and consists of experts in the field of bio-based polymer and additives, a lot of technologists, and the business management and exploitation strategies. We have done a lot of work, as I said. We're in the middle of our running project, and here we have done also a lot of exploitation activities. Just to mention that we have participated with our 5 partners in K2022, which is the trade fair, which is the world's #1 trade fair in polymers and rubbers, taking place in Düsseldorf the previous October, with 3,037 participants and more than 5 million visitors. It was a big, let's say, dissemination of our project, and our partners taking place there presented all our activities. You can see all the partners, and among all these are from different European countries. You can see the pilot lines, the characterization, the partners that work with characterization, modeling, monitoring, and also the 5 different test cases in automotive, agriculture, food packaging, construction, and printed electronics. The service providers of the BIOMAC ecosystem are of high skilled experts in the field, and they are geographically constituting, as I said, across Europe. The BIOMAC ecosystem will provide an open access to its facilities. We have, as I said, 7 pilot lines and complementary services required for the development, testing, and upscaling of the produced material in the field of nano-enabled bio-based products and materials. The pilot lines of BIOMAC cover the whole value chain from biomass fractionization, intermediate chemical productions, nanomaterials, monomers for the synthesis of biodegradable polymers, and of course for the synthesis preparation of bio-based nanocomposites. The structure of BIOMAC OETB is divided in 4 hubs. The first is dealing with biomass fractionization and nanocomposite production cluster, the materials and nanocomposite production, starting from nanocellulose, nanolignin, which are this biochar, of course, and other biodegradable polymers like polylactic acid and butylene succinate, and of course several copolymers. And the final products production for the formulation hub. All this material, for all this material, we have the quality control, the characterization, standardization techniques, and process validation. Of course, we have the innovation management, the health and safety of all of these materials. It doesn't mean that when we have a bio-based materials, this will be non-toxic and safe for the environment and our health, regulation, data management. And finally, the last hub is sustainability assessment, supply management, and circular economy. We provide several services in our project, materials, production, and technologies. In the services area concerning the circular economy, we have the circulation, the regulation, sustainability assessment, innovation management, and standardization, quality control and characterization of all produced material, process validation, modeling, health and safety of all these materials, and infrastructure, data management, value chain assessment, and quality control and characterization. Of course, for the synthesis of nano additives, nanomaterials, and polymers, we start with lignin and cellulose. With fragmentation, we produce nanolignin, biochar, of course, by pyrolysis, and from cellulose, several fragments, lignocellulose, succinic acid, lactic acid, for the synthesis of polylactite, polylactic acid, polybutylene succinate, with the diols based on succinic acid and diols that will be produced here. And of course, with nanocellulose, nanolignin, and biochar, will produce several nano composites. And all of these materials will be for UV durable resins and other applications. Sorry, for the technologies, we have screen printing, coating formulation, reactive extrusion, pyrolysis and carbonization of biomass to produce biochar, biomass fraction purification within several pilot lines, hydrothermal pretreatment of biomass, organosolv steam explosion, and fiber sludge hydrolysis, catalysis hydrogenolysis, enzymatic hydrolysis and microbial fermentation, mechanical milling for the production of nanocellulose, resin synthesis by several partners, additive manufacturer, and of course, nano-imprinting lithography by Nanotifos. Few words about the open call. BIOMAC will offer its services free of charge to 5 parties, SMEs, and other stakeholders. Startups and other companies will be chosen for the open call, aiming to upgrade existing or develop new concepts within the lignocellulose value chains of nanomaterials and polymers, starting from technical readiness level 4 to 5 and to go to upgrade to 7. Proposals for test cases can be submitted online using the application form available on the BIOMAC Open Call platform. You can find online in our website, and also Annika will present and give some information to companies that will be the rest to apply a proposal. And the chosen proposal will have full access to open innovation environment of BIOMAC, to our pilot lines, to our activities, to our products, which will advance the technology readiness level and bring them one step closer to the market. 5 select test cases will be implemented from September 2023 until December 2024. A maximum duration of 14 months. The estimated budget available for all this test case is about 1 million participating all our partners to these activities, and you can, the interested parties, companies can apply the BIOMAC the proposal from 19th December when the open call will start. And of course, each company can has an interesting idea, a concept, in TRL, some activities in TRL 4 to 5, working advanced materials and nanomaterials with relevance to BIOMAC capabilities. They will apply a proposal with the idea that we can select it, the 5 SSA proposal based on excellent implementation in BAM, and of course 1 test case per country, because we don't want to have all of these 5 proposals from the same country, and all of this will be developed from our partners and to given to the interesting parties in the company. That's all from my side. Thank you very much, I can say again, for your participation, and I can give the floor to Professor Triantafylidis for the next pilot line presentation.
Thank you, Professor. So yes, you provided a general overview of the whole BIOMAC project and on the open call, and now we will dig deeper into the specific parts. So we will have Professor Triantafylidis and George Eranio, who will guide us through the pilot lines, what the applicants of the open call can do through the services, the facilities provided by the pilot lines in the BIOMAC project. I will soon share the link in the chat of the open call, which will start, as you read before, on the 19th of December, but you can already have information. You can download the open call handbook from the link I will just share. So Professor, the floor is yours.
Thank you, Giulio. Can you hear me?
Yes.
Yes, of course.
Okay, and I guess you can see my slides also. Okay.
Yes, everything's fine. Thank you.
So, thank you very much, everyone, for being here with us today. As Professor Bikaris and Giulio mentioned, I'm going to present together with Georgia some more or less technical details about the pilot lines and their capabilities. So the pilot line hub is actually the driving force of BIOMAC, and it consists of 17 pilot lines. And as you can see, we have grouped the pilot lines in 3 clusters. As Dimitris said, BIOMAC covers the whole value chain from biomass selection all the way to final products and applications. So in the first cluster, we have the 2 pilot lines that are focusing on biomass pretreatment and fractionation. In the second cluster, we have pilot lines focusing on the downstream upgrading of the fractions, like producing nanocellulose from cellulose, or producing succinic and lactic acid from cellulose, and so on. And finally, we have formulation in the third cluster. We have formulation pilot lines and technologies aiming to the final products. I will go through the pilot lines very quickly. The first 2 pilot lines, as I said, focus on biomass pretreatment, and here we have pilot line 1 from Luleå Technical University in Sweden, with the objective of applying the organosol fractionation of biomass. It's a very neat and friendly fractionation process. It can accept several types of biomass in sawdust form, or straws, or wood or agricultural biomass, and can provide clean fractions of cellulose, hemicellulose, and lignin for downstream valorization. And this pilot line is related to several test cases and, of course, has great capabilities. Similarly, we have the pilot line number 5 from Bio-based Europe pilot plant. And in this case, these pilot plants will apply somehow different fractionation processes, the hydrothermal processes based on weak acid or alkaline pretreatment, again, providing very clean fractions of cellulose, lignin, and hemicellulose for downstream upgrading and processing. For example, cellulose being hydrolyzed to monomer sugars that will be then utilized to produce polyols and succinic acid. Going now to the cluster that works on the materials coming out of the pretreatment, we have pilot line 6 again from BEPP, where this pilot line focuses on the purification of the liquid streams coming out of the pretreatment. For example, separating sugar streams in the hemicellulose fraction, or separating sugar alcohols in the hydrogenation pilot line, as I will describe later on. At the end of the day, this pilot line will provide pure chemicals that can be used either for fermenting towards succinic acid, for example, or for using in different polymerization reactions. And as I said previously, the pure glucose or xylose streams can be utilized in pilot line 7 from ATB to microbially produce succinic acid and lactic acid that will be then used by other pilot lines to produce the prepolymers and the final composites. Here in Aristotle University, we will utilize the pure glucose and xylose streams via catalytic hydrogenation, high-pressure reactions to produce sugar alcohols like sorbitol, as well as smaller diols and glycols like glycerol, ethylene glycol, and so on, that will be used as monomers to produce the downstream resins. We will also work on the hydrogenation of succinic acid to produce alpha-omega diols, again, to be used in the polymerization reactions. Now, working on the cellulose itself, without depolymerizing cellulose to glucose, Cerise will work on fiber sludge coming from pulp and papers industry. Again, these sludges will be converted to glucose via enzymatic hydrolysis, and they will finally be fermented to bacterial nanocellulose, which will be used as one of the nano additives, nanofillers in the bio-based polymers. And talking about nanocellulose, we will apply also different approaches like mechanical milling and grinding with specific pilot lines in List in Switzerland. The feedstock here can be any different types of cellulose pulps coming out from the pretreatment pilot lines. And finally, the product will be nanofibrillated cellulose with very small dimensions. You can see here nice pictures of the nanofibrillated cellulose that can be produced, again, to be used as a filler in the bio-based polymers. Similarly, Itene, Spain, will work again on the production on nanofibrillated cellulose, as well as in the production of nanocrystals of cellulose by applying acid hydrolysis for this type of nanocellulose. And again, this nanocellulose will be used in the production of the nanocomposites. On the other hand, we have the lignin fraction coming out of the pretreatment fractionation of biomass. And here we have Creative Nano, the company from Athens in Greece, which will apply neat technologies like ultrasound-based technologies to break down lignin to smaller particles without the use of any hazardous chemicals or any other pretreatments, producing lignin nanoparticles in order, again, to be used as fillers in the production of specific products and their applications. And finally, in terms of nano additive or additive production, we have the char formation, the biochar formation via pyrolysis, which will be applied in the University of Edinburgh. The feed here could be certainly lignin, but as well as the initial biomass and other organic residues. And the final products, the biochar, can be transformed, can be activated by different methods, and also can be modified by, for example, conductive metals in order to be able to be used in the different applications like agriculture, construction, conductive textiles, and so on. Now we pass to the pilot lines that work mostly on the formulation and the production of the prepolymers and the final products. So here we have the pilot line from LIST, working on continuous reactive extrusion of non-isocyanate polyurethane materials, very important approaches in order not to use isocyanate polyurethanes. And here you see that different nano fillers will be also added during the production of the NIPUs. We also have the pilot line in Spain, AIM+, working again in reactive extrusion of PLA towards the production of the respective polymers, copolymers, and nanocomposites with all these nanofillers to be used in different final applications, like in agricultural applications and food packaging applications. We have the pilot line in Fraunhofer, WKI, which will focus on the synthesis of binder resins for coatings and 3D printing materials. The feedstocks here will be the monomers like succinic acid, and as well as the diols coming out from pilot line 3. Reactions will focus on polycondensation and polyaddition with final products like polyester resins, polyurethanes, and of course facilitating the dispersion of the nanofillers. Examples of applications will be in automotive and printed electronics. ITENA pilot line from Spain, again, focusing mostly on the formulation of coatings using the nanofillers towards enhancement of barrier properties, for example, or other activities or other functionalities that are useful in food packaging and printed electronics. We have IMEN from Spain in pilot line 15 with the objective of applying additive manufacturing in the final formulation of the products. We have 3D printing technologies of the bio-based polymers together with the included nanomaterials to formulate the final nanocomposites. You can see images of the unit here. And finally, the final products would be the bio-based polymers as well as a nano-reinforced polymers in form of pellets or filaments available for 3D printing applications. The pilot line number 16 from DTU in Denmark will focus on the development and production of flexible printed electronics using the bio-based composites, polymers and composites. And of course, different printable materials and electronic components that can be embedded into textiles will be the output of this pilot line. In closing, we have the pilot line in Greece, in Thessaloniki, from the company Nanotypos, who is applying nano patterning and thermoforming for the production of large area micro and nanostructure surfaces. Here, PLA is a very nice application, but it can also accept different bio-based polymers. The process to be applied is a blow film extrusion combined with roll-to-roll nano-imprint lithography and thermoforming. And the final surfaces are very nice, well-structured nanostructure surfaces with exceptional antibacterial properties, as we can see in the different applications. That's all from my side. Now I give the floor or the mic to Georgia to present some specific modification upgrades that were performed in the pilot lines in order to meet the needs of BIOMAC and future test case applications. Georgia.
Good morning, everybody. Thank you, Kostas, for giving me the floor. And I'm hereby presenting the plan put in place and the action carried out by the pilot lines to achieve certain objectives and to correctly fit the requirements of the test cases. First of all, what we did together with the pilot lines, we grouped them into 6 blocks according to the objectives to be achieved. And I'm hereby presenting the 6 groups. The first groups was the first group is the one including the pilot lines willing to achieve an increased production capacity per hour and production parameters. The second group wants to achieve an increased sample dimension. The third one wants to shift from semi-continuous to or batch operation mode to continuous operation mode. The fourth group is the one willing to improve environmental performance of the process to be put in place. The fifth one wants to, generally optimize the production parameters, different according to the different process targeted. And then the last one is focused on the increased feedstock flexibility and materials to be processed. And in the next slides, I want to briefly describe what the pilot lines concretely did to achieve their objectives. Obviously, this is really a quick overview, and for any insight in what has been achieved by the pilot lines, please don't hesitate to contact us, and we will give you, precise details of the achievements. So the first line, pilot line 1, managed to achieve a shift in the operation mode from semi-continuous one to a fully continuous organosolved system, adding a continuous biomass feeder with a capacity of site up to 0.5 liters of biomass per minute. Then the pilot line 2, by RISE, managed to upgrade the production capacity, installing a 600-liter reactor. Furthermore, they managed to develop a strain to decrease the byproduct formation. And then also they achieved a continuous operation mode. Pilot line 3, by out, managed with a new configuration to achieve higher flexibility and simultaneously operate the 2 main processes, the hydrogenation and hydrogenolysis. Then they managed to simultaneously process different feeds, either sugar or acid or polyols, according to the needs. Then pilot line 4 by CNano managed to upscale the ultrasonicator reactor, enhancing the power and the frequency. And then they managed to operate in 2 different modes, batch and continuous mode, with a velocity up to 4 liters per minute, thus increasing the production capacity and at the same time the sample dimensions. Then pilot line 5, BBEPP, and the pilot line 6 have 2 different objects. In the first one, the pilot line 5, implementing grinding and milling steps before the pretreatment in order to improve the biomass fractionation capabilities. Pilot line 6, utilizing tools for simulation and optimization, managed to optimize the processes to ensure the purity and recovery of the biomass fractions and materials optimization. Pilot line 7, ATB, is focused on the succinic acid production and the lactic acid production. They managed to optimize the production of the products in order to control the parameters of the whole system, and managed also to optimize the hydrolysis, monitoring the different parameters such as the specific enzyme, the concentration, the solid loading, the pH, and the temperature. Then the pilot line 8, you add in, improve the combustion performance, the online monitoring of gases emissions to the environment, and then achieve a tunable emission management system. Pilot line 9 lists in place an online monitoring via near-infrared sensor installed on the reactor extruders to achieve the optimization of the NIPU formation. The pilot line 10, against by list, put in place mechanical milling of NFC through the setup and operation of mechanical mill, resulting in optimized production cycle and product. Pilot line 11 by AIM+, increased the production capacity from just 250 grams to 10 kilos of processed lactic acid to yield up to 2 or 3 kilograms of purified lactide for reactive extruders to the NIR inline reaction monitoring. The pilot line 12 by Fraunhofer managed to install a 30-liter reactor, allowing the increase of polymerization capacity for just under 4 kg to 25 kg for a single reaction. Pilot line 13 managed to produce NFC by a continuous mechanical disintegration. An automatic feeding system for continuous production has been designed and installed, and increased production achieved up to 2 kg per day of dry MFC or NFC. Always by Tene, pilot line 14 increased the batch size up to 20 liters by the acquisition of new dispersing system to produce nano coatings with BMC. And then pilot line 15 by Amen managed to apply, install a monitoring system to ensure the quality of large size printed parts through photopolymerization and fused filament production. And then a thermal camera has been installed and tested to monitor the thermal distribution over manufactured parts. Pilot line 16 by DTI managed to ensure an automatic, faster control wash test production of printed wearable electronics. Last but not least, the pilot line 17 by Nanotypus upgrade the production, the pilot production, in order to accommodate 300 millimeter wide web PL8 films, and also install equipment to secure the quality of these films. And then roll-to-roll macro nanostructure foils are converted to sheets with the desired size formats and processed to post-thermoforming steps. So, I mean, I know that, all this information are maybe too much concentrated, but as I said, we are open to, to discuss with you further details. Thank you very much.
Thank you, Georgia. Thank you, Giulio. The mic is back to you.
Thank you, Professor, and thank you, Georgia. So now we move to the next panel, which is the next section, in which Eleonora Di Maria from the University of Padua will introduce us to the transversal services provided by the OETB. So we have seen the pilot lines, now we see the complementary service. I take the opportunity to finally share in the chat the link to the dedicated page of the open call on the BIOMAC website, where you can download the project handbook, and then you will be able next week to fill in the application, but we'll get to this at the end. So Eleonora, please, the floor is yours.
Thank you. Good morning to everyone. I would like to share some slides, if I may. So, thank you. So good morning to everyone. Welcome and I'm very happy to present to you the transversal service hubs that the BIOMAC project is offering to the applicants. I'm from the University of Padua. I'm a professor in innovation and management, so I'm more on the management side of the project. So as being said also previously, this is the picture that describes the BIOMAC ecosystem. We already listened about the pilot lines. Now we move to the other three areas, three hubs of the project that would complement the value that this project would provide to SMEs and more in general to organizations that want to use and exploit bio-based and nano material in their product and in their activities more broadly. The idea of these transversal services is that they would in some sense enrich the opportunities, not only from a technical, but also from a market point of view. The idea is that, as you have seen, there are lots of partners, lots of competencies, and the opportunity to join these OETB is that to develop and to conceive new products, new applications, but also to enter into new market and strengthen what could be the competitiveness of your potential business development also. So concerning the validation hub, which is we will follow, let's say, this circle. The validation hub is by far particularly technically connected what we have just seen. So what I'm going to present is very briefly the set of services that are included in this hub, and of course for any additional technical specification I will move the questions to my colleagues and partners that are expert in the different field of the validation hub concept. So the idea of this broad hub is that of providing support from the three layers that you are seeing in the chart concerning, examining the feedstock, the technologies and the product from a chemical, environmental and economical perspective. And the first group of services are related to quality control and characterization. From what you have listened so far, there's been really a huge set of opportunities from a technical point of view to develop and work with very different bio-based material with different characteristics, with different opportunities also of application, as we will see also later on talking about the test cases. So this service is ideally focused on providing additional support from the applicants in order to better work on the characterization of the material, try to move the products and the materials that are produced within the different final line according to what are the requests of the applicant, taking into account the fact that there could be a broad set of options based on the properties that are desired by the applicants, and so from the requests that are not only connected with what you're just experiencing in the 5 test cases, but on the other inputs that can come from the application, the open call. The second service, let's say, is connected to the fact that there will be the opportunity during the the experimentation, the use of this service to be supported concerning standards. So the idea here is to understanding and monitoring and contributing to development of standard that could be aligned with the potentialities of new material that are developed within the BIOMAC project, taking into account that the variety of application could be very different. So in some cases, the standard will already available. In other, could be specifically developed, taking into account the experimentation that will take place over the next year. The third set of services are connected to the fact that, as we have seen, there are a lot of technologies involved, different technological processes, different requirements. So from this service process validation and modeling, the idea is to provide services connected to simulation and other modeling services. And the idea is to try to evaluate and test which is the state of the system, try to consider the opportunity to have also mathematical models that could, in some sense, test in advance what could be the result of the process, and also to evaluate what could be also the consequences, taking into account the variety of conditions in which the materials, but also the technologies are implemented. We have seen we have very different, and there are a high number of pilot lines, so the requirement could be a lot. The second hub is related to the value chain. There are a lot of partners working in the different steps of the value chain. And from this point of view, the idea of this service will be to provide support, taking into account specifically the resource use, the environmental consequences of the materials, and also the application that will be developed. So here we have three specific services. The first one is the sustainability assessment. So here we have carried out, and we will be able to provide to the applicants LCA assessment. So analyzing the environmental impacts of the product through the life cycle. We know that it's not only important to evaluate the sustainability at the beginning, so as an input, but considering through all the life of the product till the end. So this will be particularly relevant to analyze which are the main drivers of positive but also negative environmental impacts, to reduce, of course, the negative one. But also this could be seen, as we will see also in the last hub, could have particularly valuable information also from a market point of view. Together with LCC, which is a very challenging but also very valuable service, the idea is to understand which are the economic hotspots during the whole life cycle, to determine which are the actions that could be implemented in order to have economically feasible production based on the technology that we've developed and taking into account the experimentation that to be implemented. The second, as the value chain hub inspire, is the supply chain management. So we will provide to the participants, to the additional test cases, decision supporting tool. So the opportunity to have an optimization model that performs an holistic view of the value chain. The idea is to maximize the value that could be provided working with different partners, different companies and research centers within the project, and together with this decision support online platform that will give the opportunity, especially to non-optimization app, the idea to get a result on the optimization process. As I mentioned, in the value chain, there is also circular economy dimension. So it's particularly relevant here. This is, since this project is an innovation process, but also has a strong sustainability goal in it, to evaluate also what are the conditions at the end of life of the products that will use bio-based nanomaterials will be provided by the BIOMAC project, to understand what could be in advance the consequences of the end of life, to manage the end of life properly, taking into account the variety of conditions, variety of application that could be involved. There will be also a comparison analysis with the current practices. And so the idea is to exploit what is already in place, which are the knowledge that the partners could provide to support SMEs and more in general organizations that will apply and will be selected by the open call in this respect. Final, last but not least, market uptakes apps. This is, as the name also is saying, the opportunity to help the companies, the organization that will be involved in the test cases, to have an opportunity to evaluate the market, to consider the development from very different angles. So one will be innovation management service. So the idea is that based on the request, there will be a development of business plan to evaluate the advantages of these new innovation that will be bring into the product in the portfolio of the organization. There will be an opportunity to obtain risk assessment, which is, by the way, very relevant when a new innovation is introduced. And also, it's really important to consider also the IPR, so intellectual property rights management. So we already are available to provide to the applicants an analysis of what are the patents already in place and what could be the freedom to operate development as an additional service. And then, of course, considering the financial opportunity to support also in the long run the process. Standards and regulation, it's really absolutely relevant. This is also connected with the fact that there are new nano-enabled bio-based and the opportunity to commercialize, to have a security, compatibility, to reduce what could be afterwards in the market, the certainty or some negative consequences that could emerge. Since there are new materials, the service, the market uptake app will provide also services connected health and safety evaluation. This is based on the analysis of health and safety risk that our partners may provide, also concerning the application based on a safe by design approach across the whole value chain to identify, which are the uncertainties, the potential risk, and of course try to avoid them, and to increase the awareness concerning the health and safety opportunities and properties better of the materials. And then the data management means providing all the information concerning all the data that will be developed and could be related with the innovation process. So thank you for the attention, and I'm going to be more than welcome to reply to any requests that may arise. Thank you.
Thank you, Eleonora. Thank you very much. So now we move to the next part, which is about the BIOMAC test cases. So these are applications of bio-based material that we have done in BIOMAC, validating the pilot lines. So I will invite Daniel Schmidt from LIST to guide us through these test cases. Daniel, the floor is yours.
Thank you so much, Giulio. And thanks to everyone here for listening and for showing your interest in our open call. So my name is Dan Schmidt. I'm coming from the Luxembourg Institute of Science and Technology, and I'm going to talk to you a little bit today about the various test cases that have already been defined so that you have some context for how you might make use of the BIOMAC services. So this is an overall diagram or chart that just shows which pilot lines are involved in which test cases. It's a bit small, and the purpose is not to make you read everything, but really to emphasize that for each of the test cases, so you see here, 1, 2, 3, 4, and 5. Let me use the laser pointer here. So test cases 1 through 5, that in each case, we are not just involving 1 or 2 pilot lines, but really very many pilot lines, something like 6, 7, 8 pilot lines per test case. And these are all working together to produce very interesting materials for the purposes of an application-oriented demonstrator. And I'll talk about each test case in particular so that you can get some idea of how this might be done and maybe get some inspiration for how we might be able to help you in a similar way. So to start out, the first test case 1, has to do with automotive applications. And in this context, the idea is to come up with a tough, flexible, abrasion-resistant material that can be 3D printed via SLA type or VAT photopolymerization type techniques, so that you have a lot of design freedom, and that at the same time is based on biomass derived monomers. So LA here refers to lactic acid, SA refers to succinic acid, and so these are being used to make polyester segments that go into a UV curable polyester urethane. There is a reinforcing phase as well, nanofibrillated cellulose, to enhance the mechanical performance of these materials. And at the same time, of course, this all has to be formulated so that it's compatible with the appropriate additive manufacturing techniques And there's a design need as well. And this is a little bit what you see here. This is an example of the computer-aided design done in this test case. So this is a sun visor cover. If you are familiar with these, of course, you know, when you want to check the mirror in your sun visor to see if everything is okay, if you're in your car or something like this, you slide this across. And these are some examples of actual 3D printed parts that have been produced using these sorts of materials generated within the BIOMAC project. So to show you how this works, the flow scheme is as follows. We start out with biomass, shown here, and you see in each case we have the abbreviation for the various partners involved. And of course, I can talk about any of these in more detail as needed in the question and answer session, but we have biomass suppliers producing the biomass. This is then being pre-treated and in some cases purified, in some cases potentially used as is. So we can use hemicellulose oligomers as an ingredient for our coatings, or we can further purify these and convert them to sugars or glucose, which are then undergoing additional chemical conversion steps to basically be turned into different monomers. So we can imagine succinic acid coming this way and different kinds of sugar alcohols and glycols or diols coming this way. And so we generate all of the feedstocks we need to make these polyester segments in this way. Then the polyester segments are put together and then converted to UV curable resins. The nanofibrillated cellulose produced here then comes in and is added to these UV curable resins. 3D printing occurs, and we end up with automotive components for interior applications, as noted in the previous slide. And so this is one example of how all of these pilot lines can come together to give an interesting demonstrator for a particular industrially relevant test case. I will present the other four as well, just so you can see how this works, but hopefully that already gives you an idea of how the overall consortium is working together, how the materials are being exchanged, and how all of the pilot lines you heard of are contributing to the eventual outcome in each test case. So we go now from automotive to agricultural. Test case 2 has to do with agricultural applications for our bio-nanocomposites. And in this case, the idea is to come up with biodegradable bioplastics, again, based on polyester type materials. So lactic acid is here, succinic acid is here. These are being used to produce different kinds of polyester formulations. And we are using additives to further gain performance in this context. So nanofibrillated cellulose, of course, is something that you can imagine might be useful as a mechanical performance additive. Nanolignin, that's NL, right, can be used to give you, for instance, antioxidant activity. And biochar, for instance, which is basically a carbonaceous bio-based material, can be used to give you a deep coloration to block UV and invisible light and things like that. And so what you see here are a couple of different relevant agricultural applications. This is a blown film extrusion process in the process of running, actually, and you can see the dark coloration in the material there. And you might imagine using such biodegradable films for mulch films in fields to effectively cover up the soil, to help to prevent weeds from growing and to allow only the plants that you desire to grow to poke through the plastic sheeting. And of course, being biodegradable, this eventually goes away in the field. And in fact, you can even use these additives as a form of enhancing soil quality as well. So that when the material biodegrades, it's actually improving the soil in the process. These are grow pots, so exactly the kind of flower pots or pots that you might use for planting plants. And of course, the nice thing about that is if you start out in one of those, you can just pick this up and put it in the field. And if it's biodegradable, you don't need to worry about taking it out again. So those are a couple of examples of the sorts of applications you could imagine. And this is the process flow scheme related to this. So you can see once more, we have agricultural waste here, miscanthus, being converted as a biomass source and pre-treated and purified. And so we have many different streams here. We have pre-treatment to produce lignin that is then being converted to nanolignin, the one additive that I mentioned previously that potentially gives you some, for instance, antioxidant or stabilization properties. We have another stream where the lignin is being converted via pyrolysis to biochar. So again, this is what gives us this deep color. And we have another stream that converts cellulose to nanocellulose, which is then allowing us to enhance the mechanical characteristics of these materials. All of these come together in a reactive extrusion process with monomers that are generated over here. So again, you can also see the feedstocks can be further treated, purified, converted, etc., to give us small molecules that can be used to produce polyesters. So we have our lactic acid, succinic acid, polyols and diols, and these are all being used either in a reactive extrusion process, for instance, using ring opening polymerization of lactic acid, or a polycondensation process, for instance, using succinic acid and various polyols and diols to make different kinds of polyesters. And all of these different biopolymers, coupled with all of these different bio-based additives, can be combined in a variety of formulations to give us some very nice materials for bio-based polymer nanocomposites relevant to agricultural applications and biodegradable in soil. So again, another example of how this can all work. Food packaging is our third test case. And here the target is transparent and compostable biodegradable PLA film. So polylactic acid again. In this case, we again look at several different additives, as well as a nanostructuration technology to achieve the performance that we would like to see. So in one case, bacterial nanocellulose is used, and this should provide a variety of different performance characteristics related to barrier properties, mechanical properties, and aesthetic properties, as well as maintained compostability and biodegradability. And in tandem, nanolignin is also used. And again, as mentioned in the previous test case as well, this material should give us storage stability without compromising the compostability or biodegradability of the plastic or the polymer. And finally, nanoimprint lithography is another advanced technique that is applied here to give a nanostructured surface to these compostable, biodegradable food packaging films that enables the surface of the packaging itself to be self-cleaning and to repel microbes, and generally speaking, to add to the performance of these materials. So that's the concept, that's the idea. And to show how this all comes together with the various pilot lines here, once more, we start out with our biomass. We have a pretreatment step where we come up with either a cellulosic stream that is producing nanofibrillated cellulose, or a cellulose plus hemicellulose stream where we're again doing a conversion process, breaking things down, and eventually ending up with lactic acid that is used to produce polylactic acid via reactive extrusion. And of course, in addition to the cellulosic and hemicellulosic components of the biomass, we also make use of the lignin-based material here. So there's an organosolv process followed by ultrasonic treatment to produce nanolignin, which is again, as I mentioned, one of our additives, giving us some stability, giving us some enhanced resistance to oxidation and degradation and things like this. And this is added in to this stream whenever we talk about making these PLA-based nanocomposites via reactive extrusion. In parallel, you can also see we have fiber sludge from the pulp and paper industry that is being, again, converted via hydrolysis and fermentation to valuable bacterial nanocellulose, which, as mentioned, is providing a variety of different performance enhancing characteristics related to barrier mechanicals and aesthetics. And this is being added into our process scheme here, once more giving us a nice high performance nano-reinforced polylactic acid formulation. And this formulation is then used as a basis for producing the packaging films that then can be directly micro or nanotextured, or you can also apply a coating to them. And so this coating can be directly based on nanofibrillated cellulose and give still more features as a means of changing the barrier properties, changing the surface characteristics of this multi-layer biodegradable packaging. And of course, as mentioned, the micro and nano texturing is what's getting us the self-cleaning characteristics, the antimicrobial characteristics that were noted previously. So at the end of the day, you have a lot of different options here. You can choose to do a single layer textured. You can do a layer that has been coated with a nanocellulose as well. You could even imagine doing something asymmetric where maybe you structure one side and coat the other. And as a result, there's a lot of versatility to effectively configure these bio-based packaging films for a variety of different applications based on all of the nice materials that are produced within the consortium. Test case 4 is the construction test case. And this test case is targeting a biomass-based bridge module, foot bridge module, with a variety of attractive properties related to UV and fire resistance, anti-fouling characteristics, and the like. And this is to be produced to be a large area multi-material additive manufacturing. So you can see an example of the sort of large area additive manufacturing equipment that might be used for this on the left. And on the right, you can see some very nice CAD sketches or CAD drawings showing the design here. So you have a honeycomb sandwich panel, and this is where some of these bio-based materials are located. And you have fiberglass facing panels on either side. And this gives a nice lightweight, high performance structure. And if we look at the process flow scheme here, the idea is that you are taking the biomass, again, pre-treating it and splitting it up into different fractions that you do different things with. So we can take the cellulosic fraction, mill it down to nanofibrillated cellulose, and that of course will give us some mechanical reinforcement for that central honeycomb layer, which is very important. We can take it and take the lignin fraction and directly use this as an additive in our, in this case, isocyanate-free thermoplastic polyurethane matrix, which is the matrix material for that nanofiller that you see being added in here. And of course, that can have some nice characteristics from the standpoint of mechanical reinforcement and again, stabilization as well. And we can also imagine taking this lignin, pyrolyzing it to biochar, and using that as a means of, for instance, enhancing the UV resistance or the thermal conductivity of the materials. And so these different nano additives are again included in an isocyanate-free thermoplastic polyurethane. So this is a very convenient material from the standpoint of additive manufacturing. There's plenty of examples of polyurethanes already being printed via AM, via extrusion type processes. And of course, polyurethanes are also known as very tough materials, very robust materials, potentially with some interesting vibration damping characteristics, this sort of thing. So you can imagine why this might make for a nice core material in this honeycomb sandwich panel construction. And of course, it's isocyanate free as well, because it's very important that we focus on sustainable and green technologies here. And so once this is all put together, additive manufacturing is carried out at a large scale using the FFF approach, and you end up with this nice footbridge prototype that I've just shown you in the previous slide. And then finally, test case 5, flexible electronics. Here, the target is twofold. First, a series of inks, because we're talking about printed flexible electronics. You can see some pictures here. So what you should have in your mind is you have a base layer, which is a flexible material. And on that base layer, that flexible material that is relatively low melting, let's say, you're printing a variety of devices. And you're doing that using a conductive ink and using a non-conductive ink. And then what you can do is tap that layer to fabric, as shown here, so that you now have wearable flexible electronics. So the base layer is something that you can almost iron on or thermally bond to the fabric. And on top of that, there is also a printed layer of bio-based conductive inks, in this case, including functionalized cellulose nanocrystals for mechanical reinforcement. Bacterial nanocellulose also can be used this way, and conductive biochar particles for the conductivity. And of course, when we want a non-conductive ink, we simply remove the biochar. We just use the mechanical reinforcing additives as needed, and we can have a non-conducting system as well. And then the thermoplastic polyurethane substrate forms the basis for these. And so to show where these are all coming from, this is the process flow scheme. Biomass is pre-treated and converted into a variety of different streams as always. So we have hemicellulose and lignin potentially used for reactive extrusion in the formation of, again, non-isocyanate polyurethanes, just as in the previous case. We have cellulose here being used in a variety of ways. We can break the cellulose down to monomers, and we can use those monomers to create polyesters and eventually polyurethanes. So think back to the first test case where we had reactive polyurethane oligomers based on polyesters that we were using as a basis for this UV type 3D printing application. Here it's a similar approach, but again, we're not using UV, we're using basically a heat cured system, but nonetheless reactive systems that are based on bio-based polyesters. And then of course we have all of our additives, various different kinds of additives. So you can see we can take the cellulose down this route, make nanofibrillated cellulose and use that in the inks. We can go this way and we have the bacterial nanocellulose coming in. These can also be used in our inks. We can use the lignin here to produce biochar. Maybe we need to modify it with a little bit of a metal coating to enhance the conductivity. Maybe not, it depends on the exact role of the ink. And so we have all these different ingredients that we can use. We have our conductive additives, we have our reinforcing additives, we have our basis in the bio-based inks, and we can formulate those in a variety of ways to make the appropriate materials for printed electronics. And then finally, this is placed on the flexible non-isocyanate thermoplastic polyurethane substrate to yield a final prototype that is a flexible printed electronic device. So that covers the various test cases that I wanted to talk about. I thank you very much for your attention. I hope this has given you some ideas as to how the various pilot lines within the partnership can be used. And I hope to have some questions from you later on. Thanks a lot.
Thank you, Daniel, for your presentation. Then I will give the floor now to Annika Frank to close this overall presentation. So Annika will guide us through the practicalities, how to apply to the open call that we have described so far. So Annika, the floor is yours.
Excellent, thank you very much. So I hope you can now see my screen.
Yes.
Yes.
Antonia, right? Excellent. Thank you very much, Julio, and thank you very much, everyone, for sticking with us. And yes, I'd just like to give you a quick introduction onto how practically you will need to apply to the open call. And just to say this in advance, don't fret, this is not your usual national or international funding proposal. So this is a lot more straightforward, you will see in the next coming steps. So just as an introduction, I want to let you know about a few important dates for the application. We will launch the open call. I apologize, this is not completely up to date on the 19th of December. So in just a few days. And then we will have a first cut-off date, which is the 30th of April in 2023. And just to quickly elaborate on this, you can submit your proposals for a preliminary evaluation by the consortium. And this will happen by May 15th. So this means you send us your proposal and we will have a look if there are inconsistencies or if the proposals are incomplete, something like this, general errors, and then you will have the chance to resubmit your proposal by the final cutoff date, which is the 15th of June, 2023. And that is really the last day where you can submit your proposals or any corrections you might have. And this is when we'll close our open call. And a few days later, a month later, on the 15th of August 2023, we will notify the applicants if their proposals have been accepted for implementation in the BIOMAC Open Innovation Testbed. And then very shortly afterwards, on the 1st of September, until the 31st of December 2024, we will have our project implementation phase where all the pilot lines and transversal services will work together to carry out your project. There's a little star here. An important thing to mention at this point, we will notify you if your proposal has been successful, and if we can implement your project, you will not receive any funding of us throughout this period. So there's no cascade funding or anything like this, which you may obviously see from other types of funding proposals, but what you will get from us is literally the entire range of services. So just to give you a quick introduction on how this is going to work very practically. To apply for our open call, you enter the BIOMAC website, our homepage, which has a designated open call section. And this section takes you to the link. This has not been activated yet, but you will see this if you then scroll down on this page, and we will take you step by step through the various procedures for the application. So I'll just give you a quick insight now into what this is going to look like, and then in a few days you can see for yourself. So the actual submission of your proposal is separated into 2 steps. Let me quickly go back to this. There is an online application form that you can fill in, which I'll show you in a second. And then there is a downloadable Word document, which you can print or just save at your leisure, fill in, and then upload back onto the portal to finally complete your proposal submission. So the online part looks as follows. You can register with the BIOMAC system. You will get a username and login, and can open the login page and portal, where we will take you to the application form page, and you can start the process. So we will basically ask you to provide some very basic information about you as the applicant. I think it's been said before, we are looking for a range of applicants. The main focus is on small to medium enterprises, but also large enterprises can apply, as well as academic institutions, research institutes, and so on and so forth. So you need to provide us with a bit of general information about yourself, about the interest in our OITB services, and the project materials, nanomaterials and polymers, and the processes you're interested in, which are provided as part of BIOMAC OITB. And as you go on, you will also need to let us know which transversal services, which you just presented, are interesting for you. And obviously, we'd like to know how you found out about the BIOMAC open call. And eventually, you will be guided to the upload proposal, which I just mentioned. So here you can download a Word file and fill this in to provide us with your actual project description and proposal. This will look something like this. So you will first need to provide us with a bit of basic information and an executive summary on the project you have in mind, and then give us various bits of information on the project, why this project should be chosen for the BIOMAC OITB test cases. You can tell us something about the excellence, about the implementation you have in mind, and the impact the project will have in total. So there will be questions on various aspects, like financing, like market entry, innovation potential. So do give us the information you have, but obviously we are also aware that your projects will usually be at a technology readiness level of approximately 4. So any information you can provide, we're grateful for, but a lot of details we will work out with as part of the actual project implementation. So you can provide us with preliminary data. And then very simply, you fill in this form, you download it, fill it in, complete it offline, and then upload it back onto the system. And this way you have submitted your BIOMAC open call proposal. And it will then go through all the steps and procedures I showed at the beginning. And hopefully if all goes well, you might be chosen as one of the test cases. And your project will be implemented free of charge as of September next year. And it's important to mention at this point that we really welcome applications from all sort of areas. Of course, some of the areas we've been looking at before for our test cases, which we established already, but also further areas. So material development, information technologies, biomedical applications, and many, many, many more. So there's no limit to this. If you work with bio-based materials, and on nanomaterial composites applications, you are the right client target audience for this open innovation testbed. And with this, I'd already like to say thank you. And I think like everyone else will be very happy to answer any questions you might have on how to apply. And generally, I think it's important to say so. I'm a project manager with the IBB. And the IBB is a single entry point for BIOMAC. So we act as the basically communication turnstile for the clients coming in we will be communicating with you and act as a mediator between you and the pilot lines and services. So any general questions you might have, feel free to get in touch with us as well. And yeah, be happy to answer questions. And pass back to Giulio. Thank you.
Thank you very much, Annika. So we are perfectly on time. So if the attendees have any questions, this is the time to post them in the Q&A box. For the time being, I will remember to all of you that on the BIOMAC website, you have a dedicated page of the open call with information, and you can already download the open call handbook, which will provide you all the details for this initiative of the BIOMAC project. This session will be uploaded soon on the YouTube channel of the BIOMAC project, so you will be able to rewatch these sessions as many times you want. Again, we have provided all our contacts, so if you have any doubts or questions regarding the open call, you can always send an email to the official BIOMAC email account. And you can also follow the development and the updates of the project on the LinkedIn page and also the other socials. Again, the open call starts, application can start flowing from next Monday, which is the 19th of December. I don't see any questions popping up, so I hope that this means that everything was clear. One thing, in the recorded session that will be available on YouTube, you will be able to jump on the different intervention with the timestamps that are provided below the YouTube description. And yeah, I don't see any other questions. So I think we can close this presentation, which will remain available to everybody. And we encourage you to spread the word on the BIOMAC open call and apply and ultimately benefit from the pilot and complementary services of our Open Innovation Testbed. Wait, let's see. We have one last minute question. As a company developing biomass derived fillers for various industries such as automotive and agriculture, Lignum will be open to discussion for European partners who would like to use materials in BIOMAC. Okay, there's an expression of interest for potential cooperation, as I understand. Okay, if there is no other question, we'll close this meeting, this presentation, and I encourage you to follow the next developments through our channel. Thank you, everybody. Have a nice day.
Thank you. Bye.
Bye-bye.
Thanks a lot.
Bye-bye to
Bye-bye.
all. Thank you very much for your participation and, of course, for all of the work that has been done so far. Thank you, Giulio, for organizing this meeting.
Bye-bye.
Bye-bye.
Bye-bye.